Hey, Dr. B here once again, and let's take a look at alkenes. Alkenes can undergo lots of chemical reactions. Their general formula is not 2n plus 2 because you lose two hydrogens when you form that double bond, so it's always just twice as many hydrogens as carbon for a monoalkene. And I hope that C2H4 shows that for you clearly. In terms of the molecular orbitals of the bonds, the hybridization of the atoms, and the bond angles, using propene as an example, we've got a sigma bond right there from the overlap of two s orbitals. We've got a pi bond here and pi molecular orbital, and since it's double bonded, it also contains a sigma molecular orbital. I think I'll leave it at that. If you see single bonds, that means the carbons are sp3 hybridized. Double bonds means they're sp2 hybridized. It's for the atoms, not the bonds. Since they only contain carbon and hydrogen, oh, by the way, the bond angle is 120 degrees for that sp2 double bonded bond angle. So right there, anytime you see that, unless it's part of a ring or something else is going on, 120 degrees. They're unsaturated as opposed to saturated. They are hydrocarbons. So there's not a lot of reactivity, but they are weakly nucleophilic at that double bond. So that double bond can come out, and I always think of it almost like a windshield wiper, either staying attached to that carbon or attached to that one, rendering you with a positive charge somewhere. If it can stabilize it, it'll form a carbocation. So the mechanism is known as electrophilic addition, meaning that nucleophilic electron-rich double bond will attack something electron poor, perhaps the hydrogen in a hydrogen halide. That will kick out that halogen. It will form the double bond, so it's swinging out, if you will, staying attached to carbon. That positive charge may form if it's secondary, for example, here, and it is. It may be a more bimolecular mechanism. If it's just a primary one, it'll definitely be a carbocation. If it's tertiary, regardless, we then have the halogen come in and attack it, and there you go. So you notice the halogen will go to the more substituted position. This will be known as Markovnikov's rule. So that is a secondary carbocation. It's a reasonable one. The reason it forms in the first place, as we've alluded to before, is because you have inductively donating alkyl groups. The more, the better that carbocation will be stabilized inductively. So there's lots of reactions, and let's take a look at them. We'll mention the mechanism briefly as we go through each one. They burn, right? Just like alkanes do. They can generate carbon dioxide and water. That double bond can attack hydrogen, especially if you have a catalyst around. If it's just H2, you can get not combustion, but you can get reduction, right? More hydrogens means things are getting reduced, and that is from an alkene to an alkane. This oftentimes can require some pressure. It can be a little scary to do these, but you can turn an alkene into an alkane by hydrogenation. That alkene can also attack bromine. So mechanistically, imagining it swing out to attack the Br, which at that point is only partially positive by a dispersion effect. But it would be a moment in time. One bromine might be a more electron poor than the other. The other one will come in and react with it, and you'll get a dibromoalkane. Br goes there, Br goes there. If instead of Br2 it's HBr, the thing can also react, but not by a symmetrical electrophilic addition, but by an asymmetrical one. First, it's going to attack the electron poor thing, that's H, but it won't attach. H won't attach there because it will. The positive charge will be stabilized at the more central position. So H will go here, and in this case, the bromine will go to the central position. We call that Markovnikov's rule. Put the halogen in the middle. We can also get these things to react with sulfuric acid in the presence of water. So the electrophile will be attacked by the double bond electrons, once again giving you a positive charge there. And in this case, we can end up with either the OSO4 attached there, or if it's just water, you can make alcohols this way. So you can turn alkenes into alcohols by having a catalytic amount of acid. Don't use too much of this, and mostly have water in so that the nucleophile can come in, OH minus, and attach to that positive charge there. So put the OH in the central position. We can also get these to react in the presence of UV light just with themselves, and they will propagate and just attack each other. This double bond attacks another double bond, and the electrons kick out to attack the next one. And sooner or later, you might get a million chained up together to make polymers. This is by a free radical process similar to the formation of haloalkanes from alkanes. Free radical polymerization. So that's a whole quiver of reactions that these alkenes can undergo.